So in particular, in this chapter, we will, well, it's called tree-based methods. And now we will be working with a different type of model for predictions. We're still in supervised learning. However, there is going to be a big difference between what type of feature we want to predict. And that's going to be that contrary to the previous chapters, where the response was a numerical value, now we can predict numerical or categorical ones. So there is also a slight note about correlation between the predictors. And usually, at least for the previous models, when we use polynomials, you do want your predictors to be uncorrelated. But however, in this case, there is a way to handle that when we're working with what is called random forests. So again, it's another plus that we get via these tree-based models. So as it says, these basic decision trees are going to predict some outcome. It can be numerical or categorical. And then we're going to compare this type of models with the previous ones that we have seen. And because of a sad consequence of this comparison, we're going to be learning about more complex models using trees. In particular, they are called ensemble methods. And they're going to be basically a way to average trees in order to improve the prediction accuracy. These are the types that we're going to see, these types of ensemble, Bayesian boosting, random forests, and BART. So let's start with what is a decision tree. So basically, we have our predictor space, our set of predictor variables. And that domain, you're going to stratify it into simple regions in the sense that they're going to be rectangles or high dimensional rectangles. So we can also think of it as boxes. We do that because such regions allow for an easier interpretation of the model. However, despite the gain in interpretation, there is a loss in predictability. So these basic models, they are not going to perform as well as the previous one using polynomials. However, as I said, we are going to combine trees in order to create new models, and then that will increase substantially the prediction accuracy. Now, for a specific example, we are going to focus on predicting some numerical variable. In this case, this would be called regression trees. In the example of the book, we have only 3 variables of interest. One is a salary of professional baseballers. We have also the years and the hits for many individuals. And so in this dispersion diagram, we can see that the coloring of these dots corresponds to the value of the salary, where yellow to red correspond to high salary, and the other ones, blue and green, correspond to a low one. Now, from this simple picture, we can see that the relationship is not quite linear. So in this case, there's going to be a segmentation of this space. In this case, it has this rectangle over here. Well, it really is the whole plane, R2, but in particular, it's only this domain, this part that corresponds to our data for years and hits. Over here is simply the description of our predictors, number of years that the player has played in the major leagues and the number of hits made in the previous year. So before looking at the diagram for this model, let's look at this stratification, this segmentation of the predictor space. As we can see, in this case, this rectangle has been split into a union of non-overlapping rectangles. In particular, this R1, that is this rectangle over here, represents what the data that corresponds to those players for which the variable years is smaller than 4.5. So this rectangle to the left. Then once we do this segmentation, we have this rectangle to the left and this rectangle to the right. And then again, we can also segment this right rectangle into two. In particular, that has been done via R2. Again, is the complement of the previous rectangle, but now also segmented via this inequality for the other predictor, in this case for hits. And again, a sort of complement with respect to the other rectangle generated via the complement of this one. That is the right side. That is just the other rectangle left that represents this box over here, R3. So that's why we meant by segmentation. In order to maintain the terminology of trees, and again, also we're working with, sorry, the term is tree because it is a tree in the graph theory sense. However, also in graph theory, we use terminology like leaves or nodes. So in particular, we label these regions, these rectangles that segment the predictor space. We call them terminal nodes or leaves. And these points, well, in this case, they say the green lines that perform the splitting of the regions, well, they are called the internal nodes. However, I will still call them regions because that's what they are, these terminal nodes. They are simply boxes. And an important note is that once you have segmented the predictor space that we have over here, now 3 rectangles, then what is the predicted value of this model? Well, it's going to be that for each region, that is for each rectangle, the predicted values, for example, in this rectangle R2, it's going to be the mean of the response for the for the observations that lie inside this region. So in this rectangle, the predicted value would be the mean of the salary corresponding to these dots over here. Similarly, for this other region, R3, the predicted value for every observation inside this boundary, inside this region R3, would be again the mean of the salary of corresponding to these dots in R3. And over here is the graphical representation of this, in this case, the regression tree that we saw when we split the predictor space into 3 rectangles. We perform a first split via this inequality, years smaller than 4.5. And over here we have the average. Well, it would not be the average salary, it's the average log salary because for that diagram, there was a log transformation for the salary variable, just in order to make it more normal, like bell-ish. So for observations that have years smaller than 4.5, the predicted value would be this. And now going to the other node, the other region, if now the years is greater, no, equal or greater than 4.5, then we have another split. So for example, for this 0.6, we would have that if the observations has a value of years greater or equal to 4.5 and smaller and hits smaller than 117.5, then the predicted value for the response would be this. And the last interpretation for this value would be that if the observation has, well, falls within this range for the years, and falls within this range, no. The opposites for hits, then this would be the predicted response. So it's just a binary selection. Well, also there is a more complete interpretation. I'm not going to read it, but that is one of the main advantages of using decision trees, is that they're quite simple to visualize, as we have seen, and also simple to, to interpret. Well, this is just a mathematical formalization of how we build this decision tree. So let's see. We started with stratifying the predictor space that is specified by these P predictors. And we did that using non-overlapping high-dimensional rectangles, R1 up to Rj. Oh, interesting. In the book and the video lectures, it did say that they have to be boxes. In particular, when one checks the, when one performs this in the practical case. Okay. Now we have boxes and predictors. So for each observation in one region, the prediction is going to be the same. That is going to be the mean of the response in that specific, for the values in that specific region. And again, we have some RSS term that we want to minimize. In this case, we are simply considering all the rectangles. And for each of them, we are considering the squared error. Yeah, the squared error. I'm summing all of them for each rectangle. Sorry, for each observation, y and y inside each rectangle. However, at least to minimize this is going to be quite complicated. It says computationally infeasible. So we consider a simpler way to do this. It's not going to be a general. And that method is named recursive binary splitting. So, well, there are two terms that describe it. That is top-down, because we start with choosing some predictor and some boundary for that predictor that minimizes quite a lot this RSS value. And from then we only make a binary decision. That is what this comes, this term over here of greedy, because, no, sorry, this is other thing. Let's see, greedy. Well, each time that we're going to split a region, we're only going to look at how the RSS is changing for that particular split of the region, instead of looking at how it's changing overall for all the possible future splits that we can perform later on. So it's going to be simply choose some predictor, choose some threshold for the predictor. That's going to give us two regions. And again, for each decision, it's going to be the same. Choose a predictor and choose a threshold. At each step, we only want to look at how this value is getting smaller and smaller as we change the predictor and the possible threshold for it. Let's see, they define, well, the threshold, they say it's called cut point. So this is what I meant, that the regions that are getting defined at it is splitting. So this is one high dimensional box. This is another, as we saw in the example before. And we want a choice of predictor and a choice of cut point, so that this specific splitting of the predictor space no, sorry, of the region, leads to the greatest possible reduction in RCSS. We're going to do this type of splitting sequentially, and we're not going to be splitting always the whole predictor space, but we're going to be splitting the regions defined by these points, sorry, by these sets. So maybe first we split this into two, then if necessary, we can split it into two again, perhaps for another predictor and another cut point, but it's always a binary split via these inequalities. So, well, when do we stop? Well, that's kind of arbitrary, but at least what seems to be the common value used in practice is that if some region that we have generated via these splittings, if some region contains no more than 5 observations, then it's time to stop. We're going to stop until every region, no region contains more than 5. So at most they can have 5 observations. And again, once we have concluded this type of splitting of the predictor space, for each region, the predicted value is going to be the mean of the observations that lie inside that specific high dimensional box. So again, with this issue of when do we stop, there is a possible problem with overfitting, and that is because if you never stop splitting the regions, then it's possible that there is a point in which every observation is inside one region and one region only. So we would have as many regions as we have observations, and that's like a complete overfit. So the training error would be 0, and we already know why that's usually a bad case. So we want to avoid having a lot of regions. In that case, we want to avoid that the tree is too leafy, too many splittings. So to avoid this overfitting, one wants the trees to have not too many splits. There is not too many regions. Well, this will reduce the variance and lead to a better interpretation of the results. And so we will perform this pruning, this subsetting of the tree. So we can start by just constructing a very big tree. That is, we don't really put quite a high restriction in the number of regions that we want our tree to have. But now that the tree has been created, we're going to get a subset of it for which our predictions are still good enough, but we now have a small number of regions. So there is no fear of overfitting the data. The way they do this selection of this optimal subset tree is very similar to the lasso regression, because we're going to introduce a penalty term. In this case, this non-negative value alpha, and it's going to multiply this value, that is the number of regions of your tree. And we do that for all the possible subsets, well, all the possible subtrees of the initial very big tree, so that a tree that has a tree that has many regions is going to be penalized via this factor. And again, as you can see over here, now this penalty term is going to control the number of regions for our subtrees. And then in order to estimate what would be a a good value for alpha in order for us to obtain our optimal subtree. Well, we do the classic k-fold cross-validation. And it's not necessary to go quite deep into it because we have already saw that technique in order to estimate the testing error. But with that, you do obtain your optimal subset tree. In particular, for the example, in the earlier parts, now we have only see a tree that had 3 regions. However, that's because that was the optimal subset tree obtained via the previous methodology. So they would start with this very large tree, and large because there is a lot of regions. We can count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Like a little bit more than 10. It's from this starting tree that we would need a good subset of it in order to get low enough testing error. And doing the methodology explained in the later slide, we can see that for these values of the mean squared error, when looking at the training error, we can see that if we consider trees with more and more regions, that if we go to the right of this x-axis, well, the training error is going to 0 because we're overfitting the data. However, for both the cross-validation and test, if we consider, for example, now what seems to be a tree with 3 regions, then now we achieve a minimum for this type of errors. But in particular for this testing error, actually the minimum occurs at 10. But if we look at the estimation using cross-validation, that the minimum does occur as 3. So that would be the value that we would choose for the tree size. That's why in the beginning we only saw a tree model using only 3 regions. That is 3 rectangles. And now we have seen that we can accurately predict, well, not so accurately, but we can predict numerical variables using trees. So that was the regression tree. Now we can predict also qualitative responses. Those would be called classification trees. Well, this is not the first, but at least a clear advantage of compared to the previous models that we saw in the later chapters about polynomial regression. So in this case, what is the change? Now, as we saw in the regression trees, for each region, the predicted value was the mean of the response for the observations in that region. Now, in this case of classification, for each region, the prediction is going to be the observation that belongs to the most commonly occurring class of the observations inside that specific region. And later on, I'm going to mention an interesting consequence of, there is something called arrow impossibility theorem. It's going to occur here, and it's going to be a very, I don't want to say sad, but it's a disappointing consequence of this theorem. Something that I will mention when we look at classification trees in the context of what is it? I don't remember the name of bagging. No, I will share the name right now to mention it later on. Okay, so what's over here? This could be the prediction for each region, the most commonly occurring class. And again, we don't have an RFS because the predictions, well, they are not numbers. So we saw for the Bayesian case, and I think in the second or third chapter of the book, we also have an analog for this classification problem, and that is a classification error rate. And well, by definition, it's a fraction of the training observations in a specific region that do not belong to the most common class. So this value over here. This would be a natural alternative to the RSS, this value that we want to minimize in order to obtain our optimal tree. However, it turns out that this value is not sensitive enough for all the possible trees that we are going to consider in order to get the optimal one. So where it should be in this slide, yeah, that we need another value to minimize. There are at least two good enough candidates. The first one is this one, the Gini index is going to be defined as follows. So for each region, you can calculate this value where PMK would be the proportion of the observations in the class K that we have inside the region, and this will be simply the complement. And we can do that for all the K classes that there is for our response variable. There is an important over here. There is an important interpretation for this value G, the Gini index, and that's going to be, well, in the book and in the videos, they say that the Gini index is a measure of node purity, but perhaps it would be a little bit more clear to understand it, that the Gini index is a measure of node impurity, because for lower Gini index, then we would have lower node impurity, and lower impurity would be also higher purity. And what we mean by the higher purity is that in that specific region where the Gini index is pretty small, where, well, in that specific region, the observations are mostly all of them corresponding to one class in particular. That's why they mean by pure. So like only one class is being represented mostly. And again, there is another possible replacement for the RSS, that is a Gini index, sorry, the cross entropy. This value over here, but they have a similar interpretation, and the accuracy of the predictions does not change as much when considering the Gini index or this cross entropy value. So let's see an example. And let's see, what do we want to predict? If the patient has heart disease or no. And the predictors that we want to consider is not only numerical ones, such as this one, this measurement of cholesterol, but for decision trees, that is regression or classification trees, we can also consider both numerical or categorical variables as predictors, as we can see over here for sex. And the splitting is quite simple. For example, let's see if there is a mention. No, so I will just show the interpretation of how we deal with the categorical predictor, in this case of decision trees. So over here, in this part, there is a region that says sex smaller than 0.5. Well, it's really just considering that there is a split between sex female in one region, well, in one subregion, or sex male in one other region. But well, that's quite simple if the categorical variable only has two possible classes. But if it had more than two, say 3 classes A, B, C, then a splitting, that is a stratifying of one rectangle, it could be something like one region is going to be all of the observations that have class A and C, and the other region is going to be the complement. So the observations that have class B. So we can still perform this certification of the predictor space, whether the predictor is numerical or categorical. That's why they mentioned over here. Okay. Let's see. In this part over here, right in the example that I was showing over here with sex smaller than 0.5. No, sorry, over here. Cholesterol is smaller than 244. Both of the regions have a predicted value of no. That is, in both regions, the most common class was no. So then why did we bother splitting that region at all? And it's explained over here, and it's going to do with node purity and how confident can we be of our prediction. So in one of these splitting of coil smaller than 244, well, they are both no, but in this particular example, for the observations in one of those regions, all of them had a class of no. So in that case, you can be very confident that the prediction would be a no. However, for the other one, I believe it was the case that it was only 7 out of 11 observations that had a class of no. So that means that because not all of the classes, not all of the observations have the same class no, then our predictions has a lower confidence. And well, and that's why they mentioned over here. And why is node purity important? Because it's got to do with how confident can we be in the predictions that these decision trees are generating. Okay. And now, lastly, for these decision trees, we compare them with the other type of models that we have encountered. In particular, these decision trees are quite easy to explain. Well, they do kind of mirror the human decision making, that is as a sequence of yes or no's. And as we saw, it can handle not only numerical predictors, but qualitative ones as well. And without the need to create these dummy variables in order to make them pseudo-numerical. However, these decision trees, they do have a lower predictive accuracy compared to the other models that we have been studying. And they are also quite non-robust. That is, if you change the training data by a little bit, and then the decision tree that you perform for that changed training data, it can be quite different as to the decision tree that we had in the beginning. So it's quite sensitive. And also, well, it's not mentioned over here, but these models, these decision tree models, they have quite a high variance. So compared to something like linear regression that has a low variance, this issue of the robustness is going to occur. So we don't want the model to change that much if the training data change, it's perturbed a little bit. And that's something that it's quite common to assume, because in the end of the day, noise is always perturbing of data. So we need that our model can be robust to those changes, that its variance is not quite high. So in order to mitigate this type of disadvantage, we're going to perform what is called an ensemble method. This really is not unique to trees, but in the general sense is that you have some building block. In this case, this type of model, these decision trees. And then you're going to obtain a powerful model out of combining many of these simple ones and performing an average of this. Well, an average, no, I'm going to leave it at that. So in particular for trees, we have this type of ensemble methods. We're going to look at bagging, also random forest, then boosting, and finally this one that is related to Bayesian analysis. So let's start with bagging. It's a shorthand for bootstrap aggregation. And again, it's a general term because it can be used for any statistical learning method. And we do that in order to reduce the variance of it. So in particular, what we cover over here for bagging and even for random forest, we could do the same for the other models that we have seen. It's just using bootstrap and using some randomness in which predictors that you use in order to mitigate this variance. However, for linear regression, for example, it already has a low variance. So, well, I have not tested a kind of bagging or random linear regression, but I would suppose that because this statistical learning method already has low variance, then applying bagging or a random forest type of procedure to it probably would not increase dramatically the testing error. But at least for this type of models that do have a high variance, then the effect, the increase in the testing error, it is significant. So, well, this part over here, I didn't quite get, because I guess that they don't mean observations for these zeta 1 up to zeta n, but they mean random variables, because in that case, it's really just what we see when we're dealing with the central limit theorem. And the main idea is that averaging a set of observations reduces the variance. So how can we do that? If perhaps, no, wait. Is averaging a set of samples reduces the variance. However, we not necessarily have access to a bunch of samples. So we can do as before, as we saw for Bootstrap, and that is simply taking repeated samples with reposition out of the single training set that we had in the beginning. So this would be the Bootstrap training data sets. We can generate some number of them, some number V. And now for each of those samples, we can perform a decision tree. So that would give us also B decision trees. So now we can define this ensemble prediction as simply the average of the predictions produced by this B number of decision trees. But that's in the case of regression, because you have over here a numerical value. So, well, you can average it. However, in the case of classification trees, well, this would be a categorical value. So again, we have B number of trees, but now we're going, in order to get a kind of average out of them, we're going to simply take the majority vote. And what is the overall prediction is going to be the most commonly occurring class among the B predictions. And this is the part when I wanted to mention this theorem that is called Arrow's impossibility theorem, because in this part about bagging and classification trees, it's like we are generating a vote, because we have, it's like if it were B individuals, each of them has some value, has some category that they are choosing, so something like A, B, or C. And out of all those possible classes, we're choosing the one that it is the most representative in the sense that it represents the majority. However, as we see with real life votes, sometimes the majority vote does not even represent more than 50% of the population. So over there is an issue of, is it really fair for something that only has, say, something like 30% of representation to be chosen as winner? And in that case, is that this theorem comes up because it turns out that if you want a voting system to at least have this type of criteria for fairness, and you can read it now, and they are pretty, well, one would totally expect that any voting system should how do you say it? That this criteria should hold for any good enough voting system. However, it turns out that if there are more than two possible choices, so like more than two candidates, then there is no, it does not exist any electoral system or voting system that holds this type of fairness criteria. And in that sense, that also limits us in the case of this bagging of classification trees, that also limits us in the sense of out of these B predictions, which one would be the best representative for the overall prediction, that is for this bag prediction. And I would guess that perhaps in any code where this type of models are how do you say, are implemented, so like in Python or R, that maybe there is a good enough improvement in the testing error in the case of bagging classification trees. If instead of taking the majority vote to get the overall prediction, you consider other types of voting systems. So something like alternative voting. It's also called ranked voting. But that would be something interesting to investigate, because I do suppose that it would lead to an increase in testing error. No, sorry, to a decrease in testing error. Okay, now coming back to the actual content of the book, it turns out that, okay. So as we saw in the other cases, you could use cross-validation in order to estimate the testing error. However, in this case of bagging, we have already enough information to model that testing error without the need of using cross-validation. And that is because, well, there was an exercise, I think it was exercise 2 of chapter 5. And we saw that for our original training dataset, for each observations, we could expect that such observation was not present in 1/3 of the K subsets that we have generated for the bootstrap to occur. So as we see over here, there is a leftover 1/3 of samples that it is not using an observation in particular. And well, you can use then those leftover samples and their respective decision trees in order to estimate the testing error, because it's almost like a type of, how do you say, leave one out cross-validation that it is occurring, because you are making a prediction for some training, for some training observations, but such prediction has not been generated. Sorry, but that model for the prediction has not been created using the particular observation that you're testing right now. And when you can do that, simply averaging the predictions for this leftover 1/3 of the samples. So 1/3 of the predictions of the decision trees, you're already estimating the testing error that you would have. And another important caveat is that despite the fact that now we have lost interpretability of our decision trees, because now it's not only one, but k of them. So these binary decisions that we saw in the beginning, it's much harder to interpret. However, we can still get a sense of which are the predictors that account better for the actual prediction that you want to have. So which are the most important predictors in your model? In that sense, over here they mention how you can do that, and it's by averaging the change of the value that you were minimizing. In the case of regression trees, we were minimizing the RSS, and for the classification trees, we were minimizing the Gini index. But by averaging those changes out of all the three, then you can get this sort of diagram in the sense that the larger value for this average of the change in this type of values, for the larger values, it represents a more important predictor. And as we can see in this example, this column of tal, I don't remember what it represented, but this is to be the most important predictor for heart disease. Okay, so that was one particular case for generating an average of decision trees. However, it's quite possible that out of all of these decision trees that we generated, that maybe they are too similar. And if they are too similar, then once we average them, well, the average is going to be similar as well. So we would like these trees generated to be actually pretty different from each other. The similarity between those trees, for example, it can occur if out of your predictors, there is one that it is really, really good. So for those trees that you are going to generate, they will probably start by performing some splitting for that strong predictor, and then again, something similar in that fashion, using such strong predictors or the ones that are also pretty good. So in order to limit which predictors that we use, we introduce some randomness, and we are going to do that because if we can make sure that the trees generated have a lower correlation between each other, then the variance of the, let's call it average model that we are going to create, the variance is going to be even lower compared to the previous example when we look at the bagging procedure. So how can we make it so that these trees have a smaller correlation between each other? Well, we're going to make that each time we are creating a decision tree, we are not going to be able to choose out of all the pre-predictors, but only out of a sample of approximately the square root of p predictors. So we don't have access to all of them, only some random sample of them. In that sense, we're avoiding this type of problem, but maybe some predictor came up a lot because it was very, very good. And now the decision trees generated are going to be quite different from each other due to this randomness. And that is enough to decorrelate the trees. If we had full access to all of the predictors, once we are performing any splitting of the predictor space, that is M equal to P, well, that is just the procedure that we have explained already, the bootstrap aggregation. So now we have to limit ourselves to a subset of the predictors. Let's see over here, they present an example where there are too many variables, so it's quite a high dimensional data set. And they limit themselves only to the predictors that have a large variance, because, well, that makes them worthwhile to predict. If it is quite low, then it does not give us good enough information to make accurate predictions. So we limit ourselves to 500 predictors, but now we compare, for example, okay. We compare what is the change in the test classification error, and we are trying to predict out of 15 possible different levels of some qualitative variable. What is this test classification error? For these possible cases, M equals P, well, that is just bugging. M equals half of P. That would be a kind of random forest. But the most common case is when you use M, that is the size of the samples of the sample of the predictors. Now M equal to a square root of P. That is the classic random forest. And as we can see, there is a decrease for this green line compared to the bugging case, this brownish one. So it indeed happened that the test error has lowered. No. No, and there was the longest line. And I saw it here. Okay, so that was it about decision trees.
Lucio?
Yeah.
Yeah, I thank you for going through this material and introducing this. We are running out of time here, so this is probably a good place to stop.
Yeah, it's true. Yeah, well, I also have to cover next week the examples, sorry, the exercises. So maybe I can do a quick summary next week of these two methods that we have not covered.
Yes.
Okay. Well then, thank you, Derek, for coming. And see you next week.
Okay, see you.
Bye.